just to introduce myself, I am Kristin Roberts. I am your open house host for this open house season, and actually every open house season, if I'm honest. I am also, in my not open house time, the public affairs director at the MagLab, which means it's my job to help tell amazing stories about the lab and the science that happens, at the lab all the time. So let's get started and really dive deeply into the world's largest and highest powered magnet lab, the National MagLab, here in the virtual sphere today. So welcome, everyone. Let's see if I can get my slides to do what they're supposed to do. Here we go. Okay, so if you came to see us on, a lovely evening, this would be the exterior of the headquarters of the National High Magnetic Field Laboratory, a beautiful building built in the 1990s, beautiful 1990s construction and architecture, and a beautiful purple sky here on this evening. This is the exterior of our headquarters facility. So the MagLab is, as I said, the only facility of its kind in the United States. It's the largest and highest powered magnet laboratory in the world. And we are lucky to be actually a consortium, really 3 different sites operating as the National High Magnetic Field Laboratory. Our headquarters in this building that you see here is actually located at Florida State University in Tallahassee, Florida. We have other facilities at the University of Florida down in Gainesville. It's about 2.5 hours away. And then about 2.5 hours by plane, we can get to our facility out at Los Alamos National Laboratory in Los Alamos, New Mexico. So all 3 sites working together comprise the National High Magnetic Field Laboratory. So in essence, this open house and this tour today is actually quite a bit larger than we would be doing even if you came to our physical building, because we'll be looking at some sites at the University of Florida and at Los Alamos that we don't normally get to see at a traditional open house. So hopefully we'll have a little bit of fun with that too. It's critically important for me to share with all of you that the MagLab is taxpayer funded. We're funded by the National Science Foundation and the state of Florida, which means any of you who are taxpayers of the United States of America or Florida are contributing to our science. And so you are stakeholders in what we do. And we just want to say thank you. And, that's why we do things like this, right? That's why we have sessions like this, is to share information about what you funded. So we hope that you're proud and excited about the work that we do. Okay, let's get down to it. Right? What's the National MagLab really here to do? What is this place, and what are we supposed to be doing? Well, actually, the MagLab is supposed to operate a world-leading user program. So we'll talk a little bit more about users in just a moment, but keep that in your mind, right? A user program, okay? We carry out in-house research. That means research that happens in our building, in our facility, with researchers that are employed by the MagLab. And we maintain our facility and develop new magnets and instrumentation. We're going to talk a lot about that today because it's one of my favorite MagLab stories. And then we do things like this. We conduct outreach and education and public information to help share with all of you the work that we do. Okay, so let's dive a little bit deeper into some of those things. Okay, so users, who are these people? What is a user? What some people don't understand about the MagLab is that we actually exist to share these amazing scientific instruments that we have with scientists from around the globe. So in 2019, which was just the last time we made this graphic, we had more than 2,000 different users from 300 different locations throughout the world who came to one of our 3 sites to conduct their own independent research. Right? That's what it means to be a user facility, to have these scientists, these researchers come and use the magnets, the probes, the other special equipment at the MagLab to conduct their own experiments. And who are these users, right? That's another question that some people ask. Most of them come from universities around the globe, right? They're professors or graduate students or, even sometimes undergraduates from other universities around the country or around the world. Some of them come from government labs, and some of them come from industry, right? From the private sector. And the thing that's important to know about how this works is that let me ask you this question, and we'll gauge what some of you know. Let me know in the chat. How much do you think it costs to be a user at the National MagLab? This is a very prestigious facility. These instruments are all very, very expensive to build and maintain. So how much do you think scientists come to have their research done here? Carlos,
so far, the answers are ranging from $1,000 to $654 million.
Okay.
We've got 2,000 just came in. Someone says nothing.
So we have some knowledgeable participants with us. So the answer is that it is free. It is free. So these scientists write proposals and they say, I want to come to the National MagLab to study XYZ material, and that's going to help the world. And we say, yes, come on, right? And they have access to the instruments and the probes and the scientific know-how built into our staff, all for free. Now, they have it for free because, remember, I told you, you paid for it. So in essence, the free comes with the price of sharing their findings, right? So they come and conduct their research, they publish a paper, and they explain what they learned. And somewhere down the pipeline, hopefully that will yield benefits for all of society, right? So that is the benefit that we all get from our investment and from making this facility free to researchers. What else do I want to tell them about users, Carlos? What else in the user story? So there's a question, is it not actually free? I mean, no, it is free, right? I mean, they don't pay for the use of the facility. Now, the only catch is if you are someone coming from industry, for example, and you don't want to publish your findings, right? You say, I'm asking a research question that is going to be really important for my business model, and I don't want to share that with the whole world, right? Because I'm going to use that, to make some money. Then there's a little bit of a different process. But actually, a lot of our industrial users, they come and do research and they publish. They publish with the world because they're asking sort of fundamental questions that benefit our world.
Kristin, we're lucky we have a user with us today, somebody that used the magnet in 2017. And then right after that, we had the question, is it free for international scientists? Well, if I remember what's been going on in the chat box today, our user is from Germany, so they are an international user. And yes, it is free for international guests.
Exactly. I'm so excited that we have a user with us here today. And, with 2,000 from around the world, hopefully we find some users, all the places that we go when we talk about high field research. And yes, it is free of charge for all users, all scientists from around the globe. There is a sort of sense of community and science diplomacy that exists around the globe when we think about sharing these research assets. And again, these discoveries help improve our whole world, right? So we'll talk more about that as we keep diving deeper into the story of the National MagLab.
There's one thing about this map that I do like to point out, and that is that there are a lot of red lines going to Los Alamos, a lot of purple lines going to Tallahassee, but not as many blue lines going to UF. And I think, and you can correct me if I'm wrong, I think that's mostly because the lab at UF is probably the smallest as far as size-wise is concerned.
Yeah, it's a very specialized type of research as well, right? So, here in Tallahassee, we're home to the majority of what, our user program represents. But there are other unique facilities, as I mentioned, at Los Alamos and at University of Florida, and they are highly specialized facilities. So when you see, lots of purple lines coming to Tallahassee, that's because we have the most stuff, right? And at Los Alamos, they're home to one facility. We'll talk about it. And down at UF, they're home to two facilities, but again, highly specialized facilities. So let's keep moving on with the story, and we can keep talking about users. If you have questions about users that didn't get answered, put them in the chat. We'll come back to them. So that other message about our kind of mission is about our role in creating these exciting instruments, right? And the MagLab is actually home to 17 world record magnet systems. So I actually sort of like to start our story there when we talk about, what are these magnet systems like? We talk a lot about magnets at the MagLab. There was a session earlier this week about magnets at Science Night, right, Carlos? And I think some people are honestly picturing giant U-shaped magnets or giant refrigerator magnets just sticking on everything. I don't know, Carlos. What are people picturing? Just giant refrigerator magnets?
You're right. They picture the U-shape, the horseshoe magnets or the giant bar magnets. And so I always have to inform them that you're not going to see a giant red and blue or red and white magnet here. Not that the color matters, but everything's going to be an electromagnet. So I'll let you take that.
Exactly. So first of all, let's start with a story about strength, because as we continue to tell the story of the MagLab, you got to have some sort of basics, right? How do we measure the strength of a magnetic field? Well, we measure it with a unit called Tesla, named after Nikola Tesla. And if you want to learn more about him, there's tons of content on our website. And in fact, we just released a brand new video demonstration of the Tesla coil. So if you want to see those sparks in beautiful slow-mo, that video is live on our YouTube channel right now. So when we think about how strong of a magnetic field something has, let's look at these charts and these graphs here that I've shared today. The Earth has a magnetic field, right? The Earth is basically a magnet. But look at how strong that field is, right? 0.00005 Tesla. A fridge magnet, those magnets that you have holding up your, I don't know, artwork or appointment reminder cards or save the dates, those are about 0.01, 0.02 Tesla, something like that. If you've ever seen a junkyard magnet that could pick up a whole car, that's about 1 Tesla. And at the MagLab, we have a fleet of magnets that range from 21 Tesla for MRI research, 45 Tesla, which is the world's strongest continuous field magnet. Out at Los Alamos, we actually have a magnet that reaches 100 Tesla in a short burst of field strength. We actually have one that reaches 300 Tesla. So we are talking about massively strong magnetic fields. Okay, that is the really critical and important story about making magnets at the MagLab. Okay, questions about magnetic field? So you can kind of see by comparison here, we can barely even see the Earth on this chart, where we have to, where we track this one only goes up to 100, Carlos. We didn't even put our 300 on this chart, but just tracking the 100 Tesla pulse magnet, we can barely even see the measurement of Earth's magnetic field.
Yeah, even if we zoomed way in on the Earth, Earth's magnetic field is still 0.00004 Tesla, so it's way down there. But one thing I do want to mention is that when we're talking about when we're talking about Tesla, we're talking about the measurement of how strong the magnets are. So we're not talking about the electric cars, though we like those and we would all like to have one. And we're not talking about the 1980s rock band, even though we like the song the way it is, but that's not what we're talking about today.
Excellent point. Excellent point. So you can find some Tesla vehicles in the parking lot of the MagLab at any moment.
Yeah, at least 3.
At least 3, maybe 4 or 5 by now. But when we're really talking about Tesla, we are talking about how strong of a magnetic field the magnet has, okay? So let's dive a little deeper and talk about how we make these magnets, okay? So these, and as Carlos said, what we're talking about are electromagnets, not permanent magnets. These are magnets that use the power of electricity, right, to create their massive magnetic fields. So what you see on the screen here, and we'll just kind of restart this zoom in, are actually the insides of one type of our magnets, right? Carlos has some on his screen as well for you to see. These are called bitter discs. And these are basically the building blocks of one type of magnet that we have at the MagLab, resistive magnets. So these magnets take, basically they take strong measures of electricity to create massive magnetic fields, right? So what we do with these bitter discs is we take them and we stack them on top of each other, hundreds and hundreds and hundreds of them stacked on top of each other in nested coils. And if you pull them apart, you would basically see that it kind of looks like a helix. So what happens is we pump electricity through these discs. You see these slits in the disc right there? You see how there's like a cut in them? The current travels around the disc, jumps to the next disc and the next disc and the next disc, right? Hundreds and hundreds and thousands of times, creating a strong magnetic field right in the center, which is what we call the bore of the magnet, right? Those of you who didn't know, electricity, magnetism, two sides of the same coin, right? So once you have those electrons moving all around those discs, you're creating a strong magnetic field right in the center of the magnet. So one of my favorite innovations and stories of the MagLab, and we'll look at these coils a little deeper as we keep going through a couple more slides, but I want to focus on this while we're on this image. So these massive holes, the big circles here, can you guys see my pointer, Carlos? Can you see what I'm pointing at? Okay, cool. So these holes right here, these large circular holes, actually help our technicians who line up and stack the discs to make the coils of the magnets. But what do you think the small holes might be for? Put your guesses in the chat right now. What are these small holes for?
I've got the smaller plate here, and unfortunately mine does not have the stacking holes, but if you look right on the edges, those little indentations are the stacking sections of these smaller plates here. And of course, you're asking about these holes and slits on these plates. Here's the other shape that we have. Mm-hmm. So the question is, what are those holes for?
Any guesses? This is, science is sometimes just about making a hypothesis, right? So what's your educated guess based on what we just talked about how these discs sort of act like the wire of an electromagnet? We're pumping electricity through the disc, massive amounts of electricity sometimes. The big holes help stack the coils together. What do you think the small holes do? Any guesses? I don't see a lot of conversation in the chat. To let the electricity flow. That's a good guess. Anybody else have a guess?
Yep, someone just typed in for cooling.
Oh, interesting. Cooling. Yes, we have
second cooling.
Yeah. We have some pretty educated participants today. Maybe it's to hold the Tesla. Okay, very interesting. I love where your brains are going today. So I will tell you these holes at their purest sense are for cooling, but we actually don't just nice job everyone. But we don't just let the air cool the magnets. That would not be a very efficient way to cool our massive magnets. For some of these magnets, we're pumping as much as 30 megawatts of power through the magnet. If you think about 1 megawatt could power about 500 homes, that's a lot of electricity flowing through these electromagnets. So we actually have to cool them with water. Who's surprised? Electricity, water. This does not seem like it makes any sense, right, Carlos? This is Science 101.
You read my mind. I was going to say, I hope she mentions this, and you just did. So yes.
Of course. So water and electrons, right? Water and electricity, not a good combination, but the water at the MagLab and the water that flows through these magnets is actually special too. It's deionized water. So it actually is water without all of those ions that you and I consume when we drink water. We can't put those through the magnets because they would actually react with the electricity, right, Carlos? And I just wanted to tell you that whole process, that deionization process, is so cool in and of itself. And we have a bunch of really cool content about that on our website if you're interested in learning more about how we deionize water. I could spend an hour just talking about that. So we're going to move on from deionized water, but we're not going to move on from this slide yet, because you will notice there's two quite different looking bitter discs on the screen, right? One of them has these small circular openings, and one of them has these sort of elongated slots. And this is one of my favorite MagLab stories, because I mentioned how powerful and how strong, how much electricity we put through some of these magnets, through these discs. I didn't mention how much water flows through, but it can be as much as 4,000 gallons per minute. That is a lot of water flowing through the magnets. So what happened at the MagLab is that they actually looked at this design of a bitter disc, which was the standard way to make magnets for many, many, many years. And they said, gosh, 4,000 gallons of deionized water flowing through this magnet per minute. This is not going super well. This is causing these discs to deteriorate and putting too much strain on these openings. So they actually modified the design of the bitter disc to move from circular openings to these elongated slots. And this here that my mouse is hovering around, that Carlos is showing you in his screen, this is called the Florida bitter disc. And it was invented at the MagLab in the early 1990s, patented, and is now the prevailing technology for magnet making, resistive magnet making, around most of the world. So, if you think about how 4,000 gallons flow through this, the way that this is engineered is really quite brilliant. The staggering of the openings and the shape and structure actually makes it a much, much stronger coil. It actually uses the pressure as a kind of a pro, right, Carlos? Like it uses it to create almost a stronger disc. So it's just an amazing innovation in engineering that was, I don't know, birthed at the MagLab, right? So yeah, in the future, when you see these circular openings of an inside of a resistive magnet, you can be picturing these elongated slots and know that that's the Florida bitter disc.
So we've got a question that I will not answer because I can show you the answer. And the question was, how thick are the discs? So I'm going to take this, and this is the A coil. So this is one of the smaller ones. And I'm just going to go ahead and start rotating it so you can see how thin it is. And there's the answer. They're extremely thin. And that's part of the reason why we're using these bitter plates, because they are so thin that we can stack a lot of plates in a small amount of space, which allows us to concentrate a lot of magnetism in a smaller space. So that's exactly why these thin plates that almost completely disappear when I hold them up, this is what they do.
So we just launched some awesome 360-degree videos on our YouTube channel. They actually weave into the PowerPoint a little awkwardly. They kind of look fisheye, but they look really cool in YouTube. And on YouTube, you can drag them around and look wherever you want. But it doesn't give me that functionality when I embed it in these in this PowerPoint. So I do encourage you to go look at these on YouTube, but I do want to show you some of the insides of the MagLab. So if we were visiting in person, you can see those helix examples on the table there where we have bitter discs stacked. So you can see the room also where they do stack these coils. This is the resistive magnet shop. Those of you that came to our sports open house actually can see the Olympic rings that were put on the up in the resistive magnet room. You can see them stacking a coil right here, actually. There's a coil getting stacked right there with the special lighting that they use. And so, like I said, I encourage you to just explore these on your own because you can drive and look wherever you want. But I just wanted to let them play a little bit here so that we did get the sense that we were actually visiting the lab today. I missed the lab. I'm sure some of you do too. This is a back room. If you've been to open house, you've never seen this because this room's not open to the public. But here's where we keep some of our spare coils and some of our spare, stacking tools. And you can actually see one of our technicians is stacking a coil right there. So some special views on YouTube that you wouldn't even have even if we were having an in-person open house right this minute. And you can see some spare coils on the shelf there. These coils will age, right? They do eventually wear out. And then we pull the coil out of the magnet and replace it with a new coil, right? That's how they are designed to operate. And so we keep some coils on the shelf so that our magnets can be ready for users at any moment when science needs to happen. See all these awesome, cool spare parts. Look at all the stuff it takes to build a magnet. It's so cool, right?
Kristin, there's a lot of discussion going on in the chat box trying to figure out exactly how thin the plates are. Do you happen to know what the measurement is? I don't have calipers with me.
Oh, I probably do. I'm sure it's on our website somewhere, but I don't know it off the top of my head.
I'm going to try and find the answer for us.
Okay, Carlos is going to dig deeper, and the rest of you just come along with me, because now I want to talk a little bit about a different way to make magnets, which we can start to see here in the superconducting winding shop, also at the MagLab. So what we've been talking about here is actually resistive magnets that take lots of electricity to create strong magnetic fields, right? But that's only one way to make a magnet. Another way to make a magnet is to make a superconducting magnet. Superconductivity is the flow of electrons without any resistance, without any friction. It's sort of like a perfect flow of electrons. But there's a catch, and the catch is that those materials only perform that special flow at very cold temperatures, right? So our resistive magnets, those discs, they will be massively powerful magnets as long as you're pumping electricity into them. Superconducting magnets, you charge them, and as long as you keep them cold, they will keep conducting, they will keep creating that strong magnetic field. So here we actually get to see in the high bay area of the MagLab. We'll keep talking about superconducting magnets a little bit more, but I just want to get back to the video. This is our high bay area. You see that giant spool here. That is actually where they have wound some cable and conduit superconductors, which use lots of superconducting fibers, if you will, kind of single coils, and jacket them together. You can see some of that kind of coil here. They're working on it as we speak, in fact. So you just get a sense of just how massive our facility is, and how some of this equipment and infrastructure can help. I mean, that big, coil there that you're seeing is pretty enormous. It's a little hard to tell in these 360s, but it's really, really big. And then all sorts of other equipment and stuff that you need to make magnets. Sorry, I'm just trying to sort of fast forward a little bit because you can go watch these for yourself after we're done. This is also where they do some of the pressure treatment and heat treatment on the magnet systems. So lots of really cool stuff that happens. And here's a glimpse of one of those coils. It looks bendy because it's being weird when I take it from YouTube into the PowerPoint. It won't look bendy when you look at it on YouTube, guys. But it is 360, so you can drag and look up and down and left and right. It doesn't keep that functionality when I bring it into PowerPoint. So, but here is one of those resistive magnet coils all stacked together. You can get a sense of kind of what it looks like. And actually, this is one of the coils for the superconducting 32 Tesla all superconducting magnet that we were talking about. Remember, superconductivity, super cool technology, but not super easy to use because it has to be kept super cold, right? Cooled with liquid helium or liquid nitrogen. So what else? Okay, so that's kind of a whirlwind about magnet making. We also make pulsed magnets at the MagLab, and pulsed magnets are sort of like bursts of magnetic field strength, right? They achieve massively high magnetic fields, like 100 or 200 or 300 Tesla, but only for a fraction of a second. So that's kind of I don't know, a whirlwind of magnet making at the MagLab. What do you want to know about magnet making that I didn't talk about? Let me know in the chat. Carlos, what did I miss?
When I started at the lab, the world of pulse magnet was still just exploding at the moment, and they were building very small pulse magnets to test different techniques, different materials, and they called those little pulse magnets, they called them firecracker magnets, because the whole job was to build it, test it, and just push it until the thing exploded. So we had these little firecracker magnets that were literally just about this big, and that's how we learned a lot about pulse magnet technology about 20 years ago when we were just testing this out. So yeah, I remember when we did the firecracker magnets, and we built them in our lab in Tallahassee and then sent them out to Los Alamos for the testing.
Yes, and they're still there. I think they're building them again now. There was a period where we didn't construct the pulse magnets, and now we are constructing them again in-house. So it's very exciting times at the MagLab. New world records. I joined the MagLab in I don't know, about 5, 6, 7 years ago now. And there was one year where in like a 24-month period, we launched 3 magnets, and it was just insane. It was insane.
That was 2017. I won't forget it. Yeah. We set the world record for the strongest water-cooled magnet on the same day that the rest of the U.S. was enjoying the solar eclipse. So that was a big deal for us.
Exactly. That was super, super fun. I think I have footage of that one in our talk today. Okay, so let's keep going because there's lots more stories to tell, and we can hop back and forth and come back to magnet making. But I also don't want to miss the point of the magnets, right? Which is, oh goodness, I went farther than I wanted to. Sorry, guys. Which is that these magnet building is amazing, and we're very proud of our magnet construction and development efforts. But there's also a point of the research that happens in the magnets, right? The magnets are tools to facilitate discoveries that improve our world. And so when we talk about those discoveries, we kind of categorize them in these very big, very broad terms, right? That we're using our magnets to explore materials, energy, and life itself, right? So at the MagLab, we actually have tons of different kinds of scientists who leverage the power of high magnetic fields in their own research questions, right? So that's the idea of these interdisciplinary scientists. I also want to touch on this word, who are coming to explore fundamental questions. At the MagLab, we do something that's known as basic research, or foundational research, or fundamental research. So these are questions at the beginning of, a material's life cycle, for example. And we'll talk more about this as we get into more details. But again, these are foundational questions that we have to understand to get into more applications in the future. Okay, so that's kind of an important piece of the MagLab puzzle. So let's dive deeper. What are we talking about when we're talking about materials? When I say the word material, some people are thinking about fabric, like material that you would use to make a quilt. In fact, these materials are kind of like the fabric of society. But a lot of the materials that we explore at the MagLab are materials that a lot of people have never heard of. So magnetic fields help scientists explore materials that are the building blocks for the technology of tomorrow. Okay, so if you picture the periodic table, those of you who are students now, you might be looking at the periodic table regularly. Those of us who it's been a while, you kind of remember these vague structure of the periodic table. At the MagLab, we've explored about 76% of the elements on the periodic table in our magnets. Okay, so if that doesn't give you an idea of what kind of materials we're talking about, I just don't know what will.
I love the fact that I could be walking in the building and run into a friend of mine. In this case, it was one of the students, Rachel. And Rachel was holding this little box, and she was wearing just very normal clothing, but walking around with this box, just kind of holding it out a little bit. I'm like, hey, Rachel, what are you carrying? She's like, oh, these are uranium crystals. No big deal.
It's true. I mean, Yes, it is so true that at any given moment, a researcher is putting a material that most of us have never heard of into a magnet to explore its fundamental properties. So I've just shared a couple of like whiz bang graphics here, but we'll dive a little bit deeper in just a second. This graphic, this beautiful kind of purple and yellowy kind of structure, is actually a superconducting material that is explored with more precision with the power of high magnetic fields. I think this is YBCO actually, which is the cornerstone of our 32 Tesla all superconducting magnet, yttrium barium
Yttrium.
oxide.
There you go.
Jinx. YBCO, yttrium barium copper oxide. So basically what that means is scientists took single elements, right? Yttrium is one of the things from the periodic table, barium is another, right? Copper is another, and they're building these kind of recipes to create new materials, right? Combining these single elements or, other mixes of these single elements together to create materials that have unique properties. This material is one of my favorites and one of the super cool materials that I love to talk about when we talk about the materials story at the MagLab. This is a sample of graphene, which is basically just a form of carbon that's been exfoliated down to a single atomic layer. Right? And it turns out that in this form, this material has all sorts of mind-blowing properties. And I just want to tell you a little bit of the story of graphene because it's like a great story in science. It was actually created by some researchers in England, I believe, who were kind of just playing with graphite and exfoliating it to see how, small they could make it, just, for the fun of it. And after they got this material that was, one single atomic layer of carbon atoms, they were like, well, that's weird. I wonder if it does anything interesting, right? So they started to explore its properties. They invented graphene back in 2005. 2004, 2005, something like that. Graphene actually won the Nobel Prize, the invention of graphene, the creation of it in 2010. We've been studying it in our magnets for, more than a decade. And most people have never heard of it when I mention it on a tour, right? But there is a lot of speculation that graphene could be a really cool wonder material that could create, flexible displays, maybe even integrated technology. So if you've never heard of graphene, when we're done today, just Google it and read some of the patents that are literally exploding in real time. I mean, when I first started at the MagLab, graphene was something like only very specialized scientists had heard of. And like today, there's something like 8,000 patents for graphene. And I don't mean like weird wonky patents from like weird companies you've never heard of, like every company you've heard of, companies you're wearing, companies you're using for your cell phone or watching your television on, they are all looking at this material. So when
Samsung is one of the big ones that they put a lot of research into graphene, and eventually what it's going to mean is that if you look at this picture in the middle on the bottom row, you're going to be able to take your cell phone and fold it up or roll it up and carry it with you, which is a crazy thing, but the technology is almost there right now.
And so I want to just remind everyone, again, we're talking about foundational research to understand the electronic properties of graphene that's important as a building block to get us to the technology of the future.
Okay. So you mentioned that this technology is blowing up, and I'm going to tell you that the chat box is blowing up right now. We've got a couple of questions, just too many for me to keep up with. So I hate to interrupt, but we got to answer some things. Kristin, can you give us a quick explanation of what superconducting materials are?
Oh, yes. Superconductivity is the flow of electrons without any resistance, friction, right? It's almost a perfect flow of electrons, but the catch is it only works at cold temperatures. Super cold temperatures have to be cooled with liquid helium or liquid nitrogen temperatures, okay? So superconductivity, amazing, revolutionary, but still some barriers, right? And some of the low temperature superconductors have to work at colder than the surface of Pluto, like negative 456 degrees Fahrenheit. Some of the newer high temperature superconductors can superconduct at warmer temperatures, but nothing like what we experience here in sunny Florida, let me tell you.
Yeah, one of the problems with video game systems is that they run so much electronics through them that they get hot and they overheat. And I remember that the Xbox had a big issue with this, with the system overheating and shutting down. Well, if you build that Xbox out of superconductors, that's never going to be an issue because there is no heat coming off the wires.
Exactly.
The next question is, why do we put radioactive stuff in our magnets, like the uranium that I mentioned?
Oh yeah, and some of you might have noticed on this periodic table example, yeah, some of the stuff that we've explored are crazy radioactive. There's a whole row of crazy radioactive stuff that we have not explored, just to be clear. And again, it's for the same reasons that we put all the stuff into our magnets, right? It's to explore and understand their foundational properties. So there's actually a researcher who's giving a talk next Friday, a scientist speed session. And he is one of the researchers who has explored some of these crazy radioactive elements. And he's actually trying to understand how they're more about their fundamental structure and properties so that we can better understand how to like dispose of radioactive elements, how to, you know, combat some of their environmental impacts. So if you have more questions about, you know, some of that really crazy radioactive stuff, bring them to Ryan Bombach's scientist speed session. And I know he will be better suited to talk about all of that than I am.
Now we do get a lot of radioactive materials that come into the lab. A lot of the materials that we get coming in that are radioactive are in incredibly small amounts. So they don't pose a health danger or a danger to the people working at the lab. So I mentioned the uranium crystals the other day, or just a second ago. And the thing about those uranium crystals is that they were crystals made out of uranium, but there was such little amount of uranium in there that it wasn't posing a major risk to anyone around them. And actually I asked, why are you doing this? Why are you building uranium crystals? And the best answer ever, and this is why science exists, she turned to me and she said, because nobody's done it yet. And that's exactly why we do these things, because nobody's done it yet. And it could be the future, it could be the next best technology, and we don't know until we try them. So don't think for a second that every experiment that we do is a resounding success. A lot of the things that we do, we're trying and they don't work out. And that's learning too, because we know what's not going to be the next superconductor. Kristin mentioned the yttrium, barium, copper oxides, the YBCO, and a lot of the new superconductors that we're making in the lab are derivatives of that, such as BISCO or REBCO, or I know Dr. Bosca mentioned 2212 the other day. I'm like, what's 2212? He's like, oh, it's the isotopic ratios of the next REBCO. And I was like, okay, I had no idea.
And there's 2223. And there's 2223, there's all sorts of things. And our scientists speak in this kind of shortcut that we sometimes have to like take them back. But I want to just clarify one really important thing, because we are talking about radioactive materials. We are talking about like some fundamental things about the MagLab. Safety is super important at the MagLab, right? Carlos and I, we take special safety training just to work in the building. And researchers that you know, work in the high magnetic fields have even more special space safety training. And we have an on-site safety team. And so things are very, very, very safe and secure. And that is a fundamental principle at the MagLab that we all take very, very seriously. In fact, if we were at the MagLab, some of you who tried to come on my physical tours, you know that actually when this magnet system, this is the world's most powerful magnet right here. When this magnet system is running, we actually can't go past gates down the hall. So some of you who've actually tried to come and see this magnet system have failed because we have such a strong safety culture at the MagLab. Again, this is going to look a little weird on my computer. It's a lot cooler when you see it right on YouTube, but we are giving you access to parts of the 45 Tesla, 45 Tesla world's strongest magnet that you've never seen before. The coolest thing about the 45T is that it's a hybrid magnet. So it has those resistive disks building 33.5 Tesla. And then it has superconducting coils making 11.5 Tesla. So this magnet's my favorite because it gets 4,000 gallons of deionized water flowing through her per minute to cool down those resistive disks. But she also operates at colder than the surface of Pluto, negative 454 degrees Fahrenheit, to keep the superconducting coils cool enough to continue to superconduct. And researchers are putting, so here we are literally like under the 45T, right? It was not running when we filmed this. That's why we were able to do it. That's why you've never been here before, because we had to take special safety training just to have access to these areas. And let me tell you, when this magnet is running, no one has access to these areas. There's also, I can guarantee you, well, maybe our user on this webinar, but I can almost guarantee you that none of you have been up the top of the stairs to the platform of the 45T. And for this special virtual open house, we are able to take you there. Again, it looks better directly on YouTube than the way that it embeds here. So my apologies, it is doing a weird fish eye thing. It's not doing that on real YouTube, I promise. But here we are arriving at the platform of the 45 Tesla world's strongest magnet. This is about 22 feet in the air. This magnet weighs as much as a small herd of elephants. And this is actually where the researchers who come from around the world work. They load their probes, they load their samples into these probes over here, and they actually put it into the center of the magnet, which is right here, accessible from this additional small staircase, where they put their samples into the center of the 45T. Again, I mean, very few people have been up here, Carlos. Have you ever been on the platform, on the little staircase to put your probe?
I've been up there next to, never directly on top of that magnet. And I've only been up there a couple times and not very recently.
So I have to tell you, this is some exclusive access that we are giving you here. And I want to tell you, this isn't just cool because this is a massive magnet, right? But let's talk about graphene again. Graphene, again, remember that single atomic layer of carbon atoms. If you looked at graphene under a microscope, you would see that it kind of looks like a honeycomb pattern. But when you look at graphene in a high magnetic field, you can actually see the electrons and the way that they move and flow through the material. So it's almost the difference between, seeing a still picture and seeing a video, right? Something in motion, something living, and the way that it's operating when it's alive. And that is the power of high magnetic fields, right? That is the power of research in high fields. I also want to mention the pulse field facility. This is a glimpse of that 100T pulse magnet. Super, super, super cool. Again, it's a burst of magnetic field strength to create 100 Tesla for a fraction of a second. The 45 Tesla can run for hours and hours and hours and hours, as long as you're pumping 33 megawatts of power into her. Remember, 1 megawatt could power about 500 homes, just to give you a sense of how much power that is. If you want to talk more about the pulse field facility, the magnets they have there, the research they conduct there, we're going to have a scientist speed session with Dr. Laurel Winter on March 1st at 6:30 p.m. Eastern time. Come back and bring all of your questions to her, okay? She is wonderful, brilliant, and I would love to have you guys come back and talk about pulse magnets there, because I'm running so over time, Carlos.
Well, speaking of questions, excuse me, one of the questions that we got in the chat box is, how do we get individual atoms to do what we want them to do? Which is a great question. And I can only answer by saying this. There is physics going on at the lab. There is chemistry going on at the lab. And oftentimes they're mixed together. And this is a perfect question for Dr. Ryan Baumbach, because he will tell you how he's able to strip away all the materials and work with individual atoms, because I'll be honest, I don't know. So you're going to have to ask Ryan that question. Also, our user that is in the in attendance today used the 21.1 superconducting NMR magnets.
Oh, cool. We're going there next. We're going there next.
So she had never seen the hybrid, and she was like, this is so cool. And she was just jumping off to the YouTube channel to see it all going on at the same time. So even our users are excited by the magnets that they didn't get to use, which is awesome to say.
I'm so excited. And I have to tell you, you know, this is exciting for me too, right? We've been away from the lab, working from home because of COVID. And this virtual tour is reminding me even about all the things that we just love about it, right, Carlos? It's been a while since we've walked through these parts of the building. Carlos mentioned that 41.5 Tesla magnet system that was launched on the day of the solar eclipse in 2017. This is a picture of it right here. There's a 360 video of it on YouTube. But this is a great picture, I think, to just see what the MagLab looks like when science is happening, right? It's kind of a mess. There's some researchers over here looking at a computer, looking at a material under the microscope, right? They've got their probe is inside the magnet right here. You can see it kind of sticking out of the top there. They've just worked on loading that probe on this table with the microscope. Remember, their samples are very, very small. These magnets are creating massively strong magnetic fields in the center of the magnet, which is only, you know, millimeters wide, 33, 40 millimeters sometimes. So these are very massive fields in very small spaces because we're channeling that power to explore the structure of these materials. But I love this picture because on any given day, if you were touring the MagLab and science was happening, this is basically what it would look like, right, Carlos?
Yes, it would. A couple questions that have come in. Somebody wants to visit this year. Hopefully at the end of 2021, we should be able to have guests come through the lab and do tours again. Somebody wants to know what happens if you do not use the full 30 megawatts of electricity through the magnet. So if you use less electricity, you're going to get less magnetism. So the magnet will still be working, but it will not be as strong as it would be with the full amount of electricity.
These are questions. Great questions, everybody.
Somebody wants to know what else can we do besides magnets? Well, what we're doing is we're actually using the magnets to do other things. So the magnets are tools. They're not everything that we're working on. We're using them to learn about all sorts of stuff going on around the world. And that's all the questions we've got now.
And there are other applications for magnets that we can talk about at the end, right? Like some of our researchers are looking at, you know, superconducting applications beyond the traditional magnet structures that we've talked about. So we'll save that conversation for the end because I have to talk about life and energy and all of these amazing details about what the magnets are doing. So on the other side of the building of the headquarters facility in Tallahassee, Florida, Florida State University, we're using magnetic fields to help scientists understand the structure and function of chemicals and cells, right? These cells are central to life, both when healthy and when under attack by disease. So this is kind of a fancy way of saying, like, we are using these magnets to understand the body, the diseases, all sorts of really, really critical things. And in fact, we're actually using these magnets to understand tuberculosis, Alzheimer's, Parkinson's, HIV/AIDS, cancer, migraines, traumatic brain injuries, and yes, even COVID-19. So there's a series on our website if you're interested in seeing how high magnetic fields are being brought to bear in this battle against COVID-19. You know, go check that out. There's some great stories of researchers who are coming to the MagLab to do this kind of work. So I want to I don't want to fly through this, but here is that 21 Tesla. It's a little blurry on this screen, huh? The 900 megahertz ultra wide bore NMR magnet. This magnet has kind of a special superpower. And I want to tell you about what it is, because if you've been to the hospital or a doctor's office and you've had an MRI, you have actually been in the center of a magnet. You've actually been in the center of a superconducting magnet. How about that? But that magnet is only about 1.5 Tesla, maybe 3 Tesla if it's pretty new, pretty state of the art. At the MagLab, this magnet, this MRI, is 21 Tesla. Okay, so when you think about hospital MRI, 1.5 to 3, 21 Tesla. Well, what's the benefit of higher magnetic fields? Here it is. It's twofold. Thing number one, you get ultra clear resolution, right? So you see this image that I'm circling right here. This is actually a rat brain. And you can see with such clear, crisp precision what you're seeing there, right? So this is kind of like, if any of you are old enough to remember a time before, HD TV, right? If you remember what old televisions used to look like, and now we've got these super, super high resolution televisions. It's sort of like that. That's one superpower, where we get that really clear, crisp resolution. But I think this magnet's really special superpower is its ability to image things that you just cannot see at lower fields. So what kind of things am I talking about? Well, it turns out that researchers studying on the 21 Tesla MRI magnet, NMR magnet, can actually see sodium, potassium, lithium, right? These are things that are too sensitive to see at 1.5 or 3 Tesla. So why do we care about seeing those things? Well, some of our researchers actually think that imaging sodium in tumors might be able to tell us whether a tumor is resistant to chemotherapy before treatment begins. It could tell us within 72 hours of finishing chemotherapy whether a tumor begins to shrink, right? Whether your chemotherapy worked. There's even some researchers who are speculating that if you could create a sodium imbalance at the cellular level, you could break apart the tumor without chemotherapy at all. There are remarkable things happening when it comes to MRI and MR work at the MagLab. Carlos and I spoke to a researcher last week, right, Carlos, who was looking at sensory proteins, right? He's using nuclear magnetic resonance to understand our senses and how they impact health and disease in the body. There are amazing, remarkable things taking place here. Now, I want to be clear.
Since you went ahead and you mentioned the sodium and the other materials, this is the magnet that our user that is with us today. And by the way, I love that she is here and giving us all this great information. Fluorine was what she was working with, so she had to mention that too. Working with our friend Jans, who we both know and have worked with in the past too.
Yes.
And one of the questions that we've gotten in the chat box going the other way, somebody asked, what if we use less than 30 megawatts in the DC magnets? They want to know what if we put more than 30 megawatts into the DC magnets? And that's where things get kind of tricky, because putting too much electricity into the magnet is going to cause the magnet to overheat. And that can be catastrophic for the magnet, right? The magnet will actually start to overheat and could melt down. And so bad things are going to happen if you put too much electricity into them. However, we have a staff that is dedicated at watching all the measurements coming through, and a computer system that is built to do that too. So if the magnet starts to overheat in any way, shape, or form, it's going to shut down the magnet before it damages itself. So that's not something that we're too concerned with happening, though, to be honest, it could happen.
These magnets are finely, I mean, remember, these are high precision engineered instruments, right? So they are made to take as much power as they can and no more, right? And there are many, many systems in place to ensure that they get exactly what they need to operate the way that they should. There's a great feature called Team Tesla, Carlos, on our website that talks about how we keep these magnets in shape, what we have to feed them, how they're trained. So I just want to remind everyone again, years of engineering go into these magnet projects, right? This magnet that we're talking about right now, this 21T, is home built, home designed. This is fundamental work that took decades to explore, right? That's why you can't just go buy a 21T off the shelf. We designed and built this one specifically at the edges of what is possible, so that researchers like our user on this tour can come and make experiments that you can't do anywhere else in the world, right? I want to know, fluorine, that's so fascinating, but I want to get back to this magnet and just clarify something. These biological systems and diseases that I'm mentioning, we most closely associate with humans. However, this magnet does not research humans. The 21T, even though it has an ultra wide bore, is only about the size, the opening is about the size of a Florida orange or a grapefruit. So it's only about this big or so. So what we are able to image in this magnet are rodents, rats, birds, other small mammals. And we use those preclinical models to help make discoveries that are translational into future applications. So again, remember, foundational research, even though it sounds more applied when you're talking about diseases like tuberculosis and cancer and COVID, but again, these are preclinical animal models. I want to tell you, the animals are fine. They're alive. They go into the magnet alive. They're in a very specially designed probe. There's lots of rules for scientists who use animal studies. We follow all of those rules. So that is a really important detail. We can't make it bigger. This is a great question, right? Why can't we just make it bigger, right? Why can't we put humans in there? Make the opening bigger. So creating a strong magnetic field, remember what we talked about in the magnet design conversation, we can only have openings that are so big because we want to channel all of those electrons moving around for the power of a strong magnetic field. If you make that opening bigger, you can't create as strong of a magnetic field, right? So when you think about that human MRI that we talked about that's available at a hospital or doctor's office near you, that's why it's only about 1.5 Tesla, 3 Tesla, because it has to be big enough for me, and it has to be big enough for, the football player down the street from me, right? That has to have an opening large enough for humans to go inside. I will tell you, there are some powerful human MRIs that are under development at research facilities and other universities. I spoke to a researcher in Chicago, I believe, who has a 9 something system, and there's a researcher in Minnesota who has a 10.5 Tesla system. These systems are only large enough for the human head, and they are not like clinically available. So that is definitely a battle in the quest for the future of high field magnets, is how strong of a magnet can you make with how big of an opening, right, Carlos?
Yeah, Kristin, I actually want to go back to the animals for a second, because you mentioned the probes, and using your mouse, can you show us where the probes are? Because some of them are visible in this picture.
Sorry.
They are right over there, right? So those are the probes, some of the probes. We got a lot more, but those are some of the probes that we've got. And this summer, we were, during the summer exploration series, we were actually interviewing one of the NMR scientists. Actually, I'm sorry, he's a postdoc. And what he was working on was live animal NMR. And so my students asked him, like, what scares you the most at the lab? And he said, the rats. And I go, well, how do the rats scare you? He goes, oh, because they'll bite you. They will absolutely bite you. And I was like, okay, that's a hazard I had not thought about happening at the lab. So what happens when we put the animals into the magnets? Quite often we'll give them a little bit of medication and put them asleep, so that they go in asleep and they come out asleep, and they're resting the whole time that they're in there. And I have additional information from our user who says that they will only bite if you bother them.
Yes, important information. And I just want to clarify, this is special to be able to image something while it is alive, right? You're not looking at disease pulled out of a living organism to see, what it does outside. You are looking at the way that it interacts with a living organism in vivo. And that is one thing that's really, really special about this magnet system and about MRI in general, right? Before there were MRI magnets, people had to do something called exploratory surgery. They'd say, let's just cut you open and see what's going on. And so even just the invention of MRI and the widespread availability of MRI is an innovation in magnetic field technology. So also I could talk about life all day, but again, there's another exciting magnet development in this space. Maybe our user is looking forward to time on this magnet system as well in the future. This is the 36 Tesla series connected hybrid. And it is actually a remarkable instrument as well for nuclear magnetic resonance research. Very high sensitivity, high homogeneity or sort of stability, if you will. And there is some speculation that they might be able to do imaging on this magnet in the future. So stay tuned for even cooler life-related research to be coming out of the MagLab soon.
I am told about that rumor, and going back, I think from what I was told was that the 21 Tesla magnet has a resolution of 900 megahertz. the rumors that this might be able to do imaging at 1.8 gigahertz, which would be amazing. So something that we are working on.
Exactly. So, that's under development right now and exciting research to come. I told you we were going to get to go down to Gainesville today, down at the University of Florida. Our AMORIS facility, Advanced Magnetic Resonance Facility, is part of the McKnight Brain Institute. And this is one of their MRI systems. Their systems aren't quite as powerful, but they do have larger bores. So, there's all sorts of things that researchers are shopping for, right? I want really, really high fields. But I have to get a really small bore, right, as center of the magnet. Maybe I want to image a larger animal model, but I can't get all the way up to 21 Tesla. Maybe I can only go to 11 Tesla or something like that. So this is a glimpse of one of those instruments at the University of Florida. And just because we're already at an hour of our session, I want to keep going, but please keep asking questions. I want to talk a little bit about energy research at the MagLab as well, because this is critically important too.
Quickly, let me get a couple questions in. Can a human have any side effects from using an MRI scan?
So, MRI is not like X-rays, right? You're exposed to magnetic fields all the time. Everything where electrons are moving have magnetic fields. The Earth has a magnetic field. This light that I'm sitting down in front of has a magnetic field. And so, no, there are not human impacts on from MRIs. Although there is some interesting work about how to load a human into a massive MRI and the loading time that is of most comfort to humans. So there's some, with these state-of-the-art systems, there is some work that has to be done to just make sure humans are as comfortable as possible. But no, you don't have any weird effects.
One more quick question. How long does a 300 Tesla single turn magnet last? And I had to, no, don't worry, I had to look it up because I didn't know either. It's 5 microseconds.
Woof. So very, very short. Okay, so let's move on to energy research. It sounds like some of our participants, are concerned about our length here. So let's get into this. Scientists are also using high magnetic fields to analyze and understand energy sources, right? For green, renewable energy. So let's talk about the magnets that we use for this. Here is another 21T down the hall from the one we just looked at. This is the 21 Tesla Fournier Transform Ion Cyclotron Resonance Facility magnet, which is kind of a mouthful. We had a scientist speed session with a researcher who studies on this magnet system the other day, and she basically told us this is like a fancy atomic scale, right, Carlos? And basically what they do is they put very, very complex chemicals into this magnet, and they're able to weigh them with extreme precision, down to a billionth of a gram precision, right? And because they're able to weigh them like that, they're able to understand the chemical makeup of really complex substances. So something like petroleum, right? Something like petroleum-based products can be comprised of 100,000 different chemical components, right? And with magnets like this one, we can actually understand the recipe. So if you have a really good recipe, then you might be able to say, well, where can I substitute applesauce for oil in my recipe? Where can I substitute some ingredient in this petroleum for something that's greener or more renewable? So that is one way that energy is being explored. If you want to learn more about this magnet system and some of the work that happens here, there's actually 2 sessions coming up on March 4th. One of them is about chromatography, and we'll be making chromatography butterflies. And one of them is a kitchen chemistry session where we'll be using the kitchen to explore different chemical processes. So, again, the other energy lesson here is actually in superconductors too, because superconductivity, if we could harness it with just the right precision, find a superconductor that works at warmer temperatures or at lower pressures. There are some superconductors that work at warmer temperatures, but under extreme pressure. So we've got some stuff to balance there, but we could change our energy portfolio completely with superconductors. There's also work at the MagLab to explore lithium and lithium-ion batteries and how lithium flows and discharges through the magnets. And researchers here are also understanding the environmental impacts of different, complex chemicals on our environment. There's a great article about asphaltenes and asphalt that comprise our roads all around the world, and some of the kind of maybe not so great chemical impacts that are happening there, and oil spills. We've done research on different oil spills as well. I want to make sure to plug some of Carlos's programs. There's camps and internships and research experiences that you can take part in around the MagLab. This is a glimpse of our staff before COVID on one random day where we all had a photo to celebrate our 25th anniversary, which was last year. Some of my favorite obscure facts about the MagLab. We have had over 25 years. Our 25th anniversary was last year, but we've had more than 25,000 researchers come and conduct experiments from 54 countries and 50 states and territories, more than 100 patents, almost 10,000 publications, 30 different languages are spoken at the MagLab. At open houses over 25 years, we've had more than 100,000 visitors come and see us, 2,000 students who've been campers, 2 weddings. And then you can also see the coffee and pizza that fuel the science that happens at the MagLab here. Those are sort of more estimates, but we think that that's probably about right. We are also supporting industry in the magnetic capital here in the Tallahassee, Florida area. If you want to talk more about STEM and entrepreneurship, there's a special session for that coming up this week. And again, I mentioned all of you are stakeholders in the work that we do. We take that very seriously, and we're proud to create more than $100 million in economic output for Florida and the United States annually. And later today, we'll be having our first escape room session. So I hope I see some of you to help explore the escape room. If you can't make it today, come back on March 4th, Thursday night. We'll be having game night at 7 p.m. Here's how to stay connected with us. And I'm going to call that the end of this tour. And we will be happy to, if I can stop sharing my screen, we will be happy to take some questions for anyone who wants to stick around and talk more about magnets. But I hope you've kind of gotten a sense of, what the MagLab is like and how we, explore all of these amazing materials with the power of high magnetic fields. Woo, that was a whirlwind, Carlos.
I mean, you could easily spend half a day walking around the building and talking about all the things. We didn't get to mention the no diving sign, which is one of my favorite parts of the tour. We didn't go into Millie Kelvin Jr., which is one of our brand new offshoots, which is a Faraday cage that we built with Millie Kelvin magnets inside. So,
and that's all, all of those are available in 360 right now. I will put it in the chat for you. You can go into Millie Kelvin Jr. You can see the Faraday cage screening on the windows. You can look at the new 32T magnet system. It is all there for you live in YouTube. I just put the link in the chat.
And I'm about to share the link to the MagLab open house page so they can see the rest of our sessions coming up. But I think that wraps it up for us. So thank you everybody for joining us.
Thank you so much, everyone, for coming on our guided tour. We hope to have you back at the physical MagLab sometime soon. And we would love to have you, all of you, come and visit us in real life. But it's been fun to visit with you in the virtual space. Stick around. As soon as Carlos ends the chat, we are going to see you're going to see a short survey. We'd love to know what you thought about this session, how it went. And I hope to see some of you at the escape room in a couple of hours. Come back and see us. Thank you. Take care.